Okay, so I pretty sure I just discovered a algebraic property for the mixed hyperoperations. So new algebraic property for mixed hyperoperations. And I am a little bit excited, and I kind of wish I could be more exact about what it is. Um, but no, I kind of wish I knew how to publish a paper about it, but I don't, so I'm putting it on YouTube. I also am kind of impatient, so I'm putting it on YouTube. Of course, I haven't done much research on it. So I don't know how to prove this, but I'm pretty sure it's true. Um, and what this is so to this algebraic property, it's pretty interesting, I'd say, once you explain it. So to just put it quickly, the double left pentation of 2 equals is the same. So if you ugh, the double left pentation of 2, so LLX is how we'll represent that, x being the variable, is the same as the um, as the left pentation of the right tetration of 2. So that's maybe pretty complicated. Um, so this maybe needs explaining if you're not familiar with hyperoperations in general. But basically, the hyperoperation hierarchy, let's start at the bottom here. It starts with addition. Um, it starts with addition, and basically how the hyperoperation hierarchy works is that you will iterate the previous function to get the next function. So whenever you iterate addition, and that's represented by this up arrow right here, you of course get multiplication, um, which is usually drawn, which is usually we usually use an x for multiplication. And then if you iterate multiplication, you will get exponentiation. So if you iterate multiplication, you get exponentiation. Now, you can iterate exponentiation to get larger hyperoperations, but but it very quickly becomes useless for multiple reasons. It's because hyperoperations, they just grow so fast that numbers get too large to use, and also because exponentiation is not commutative, you can, unlike the previous operations, you can iterate it in 2 different ways. And that is and those 2 different ways are called left tetration and right tetration. So the way that right tetration works, which I will represent as this R with a little hat on top. So the way that right tetration works is that, yeah, right tetration is that you take a power tower, let's say of 2s. This is really hard to do on paint.net. And this power tower is, exponentiation. And you start at the top, so you start up here, and then you simply compute it going down the tower. So that's right tetration. Left tetration is just going the other way. You're iterating exponentiation, but you're going the other way. And that will get, um, so this is my little symbol for left tetration right here. And here, all you are doing is you are taking the same power tower of 2's, but you are reading from bottom to top. So uh, you are doing 2 to the power of 2, and then the power of 2 then you are squaring that. Whereas here you are raising 2 to the power of 2, and then whatever the result is, you're raising 2 to that. So very different. They are very different. Um, and one, okay, so the issue with these hyperoperations is that we don't really know of many algebraic properties we can use to understand these and larger operations. Um, and because they just don't have much. Right tetration specifically has just one algebraic property, and it's called the recursive property. And every single hyperoperation has the recursive property. And all the recursive property really is that if you take a given function, so basically just take a given function f, and it operates on x. So the recursive property is basically just saying f of x is equal to, since these hyperoperations are ordered, f minus, it's equal to, so these are two values. The recursive property is basically like 2 tetrated to the x, or no, x right tetrated to the y equals x raised to the power of x right tetrated to the y minus 1. That's all the recursive property is. Every single hyperoperation has a recursive property. It's not exactly the same in each one, but because of how the hyperoperations are defined, every single hyperoperation automatically gets the recursive property, allowing you to express it in terms of a lower operation. But all that the recursive property allows us to do is, if we know the result of a function of x raised to a certain power in a hyperoperation, we can figure out what it means for x to be raised to the nth minus 1 power. That's all it really does. It doesn't do much for us. And so what we want to do is we want to find other algebraic properties that do more. Now, left tetration, because it grows so slowly, has a additional hyper operation. So left tetration right here, this is equal to saying x. So x left tetrated to the y, which will represent as that xly, is equivalent to saying x raised to the power of x raised to the power of y minus 1, which is a much more powerful property and shows you that really left tetration is really just a variation of exponentiation. There's a reason that the canonical hyperoperations are the right operations. It's because they grow faster. So right operations are faster and less similar to previous operations. And so these are often considered to be the right operations are something like the canonical hyperoperations, whereas left operations are considered alternative, slower, and more similar to previous hyperoperations. But they aren't just more similar to previous hyperoperations, they also turn out to be more similar to one another. So if you take each of these hyperoperations, left and right tetration, you can make two new hyperoper two new hyperoperations that are iterated versions of both of these. Um, and the way that this works is I'm just going to represent this as you now have you now do pentation. So, and this is how I'm going to represent them. So, um, I definitely want that. Uh, I'm sorry with how long it takes to draw these. I am just kind of like suddenly realized this and I'm just doing it, if you know what I mean. Um, so we got. So whenever we have, these operations of tetration, both left and right, we can iterate these as well. And when we iterate them, we also have the option of reading them from top to bottom or from bottom to top. So uh, I'm just going to stop putting the cap on these. I think if you understand what hyperoperations are, you understand what I'm doing by writing these L's and R's. So I'm going to stop putting the caps on them. So the we have the option of reading them from bottom to top and from top to bottom. Reading them from bottom to top means that we're doing a left hyperoperation, and reading it from top to bottom means we're doing a right. And that's because if we lie them down flat using regular Knuth arrow notation, reading them from top to bottom is the same as reading them from right to left. In Knuth arrow notation, and likewise, bottom to top is the same as left to right. And this produces, and so whenever we are taking the tetration, there are two variants of tetration. But there are four variants of pentation, and all of these functions are unique. But it turns out that for one number in particular, two of these operations are actually identical. And that is for double left tetration and right left tetration. When we take a power tower of twos, or no, whenever we use two and we do like double LX, whenever we take the left tetration of two and have a particular power x, that is equivalent, the exact same thing as taking the left tetration of the right tetration of 2, and only 2. And how does this work? Well, basically what's going on here, let's just get a new layer. what's going on here is that whenever we take a power tower of 2's using the whenever we do the double left pentation of 2, for example, let's go with two double left pentated to the 4. This is hard to say. This is essentially the same as saying 2 left tetrated to the 2, left tetrated to the 2, left tetrated to the 2. And we're reading it from left to right. And there are a few properties that you need to be aware of. Whenever you have 2, any hyperoperation and 2, H is just being used as a general operation symbol, that is always equal to 4. So whenever we have this string of 2, L2, 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 reading it from left to right, what do we get? We get 4 left tetrated to the 2, left tetrated to the 2. Now the next step on this journey, 4 left tetrated to the 2 is going to equal 4 to the power of 4, 4 to the power of 4 left tetrated to the 2, left tetrated to the 2, and that is going to, of course, equal 256 left tetrated to the 2, which is going to equal 256 to the power of 256. So this is what we do. This is what the double left pentation looks like. Now, when we do the left pentation of the right tetration, which I'm representing as RL, since we first go up a step to the right and then take a step to the left, what this looks like is 2R2, R2, R2. But remember, we're reading this from left to right. We're not reading this from right to left. And so what does this look like? Well, any 2 hyperoperated to 2 is just equal to 4. So this is 4, R2, R2. Now, another thing that I need to say is that 2 left is that any number left tetrated to the 2 is equal to any number right tetrated to the 2. And that is because whenever you, in both cases, this is equal to x raised to the power of x. And what that means is essentially that, and whenever you have x tetrated to the x, whenever you just have 2 elements in, exponentiation, hyperoperation, and both of them are the same, it doesn't matter which direction you read it in. So left tetration and right tetration are identical whenever the power is 2. And what this means is that 4 right tetrated to the 2 is equal to 4 to the power of 4 right tetrated to the 2, which is equal to 256 right tetrated to the 2, which is equal to 256 to the power of 256. And if you note, these are equal. Now, obviously, 256 to the 256 is a bit too big to compute, but it's 2 to the power of 2048. But what I want you to see here is that this is not a fluke. This is not a fluke at all. Because if we were to take 2 double left pentated to the 5, and 2, doing the left pentation of the right tetration, and we do that to the 5, both of these equal the same thing, which is 256 to the power of 256 to the power, and that has the right tetration of 2, and then this is equal to 256 to the power of 256 to the left tetration of 2. And those both equal because because again, anything left tetrated to 2 is the same as anything to the right tetrated to 2, because this is just equal to 256 to the power of 256 to the power of 256 to the power of 256. Okay, that's a bit complicated, but I hope you see what I am seeing. The left pentation of 2, the double left pentation of 2, is the same as the left pentation of the right pentation of 2. It's not that just that these two numbers are equivalent. 2RLX, these two functions are equivalent. And I hope you can understand my notation here. These two functions are equivalent. But it doesn't just stop here, because there is also what you would call, this itself, this actually extends to higher hyperoperations. And I'm just going to represent the hyperoperations as dots here. But basically, are just circles and lines. This extends further up the higher hyperoperation hierarchy. And how does it extend further up the hyperoperation hierarchy? Well, anytime you take two lefts basically, the way that extends up, I'm sorry I'm being so slow with this setup, is that whenever you are dealing with putting 2 at the base of a function, anytime you take 2 steps to the left, it is the same whenever it comes to hyperpowers of 2 as taking a step to the right and a step to the left. So this doesn't just mean that the double left pentation is the same of 2 is the same as the left pentation of the right tetration. It's also the case that the double left hexation of the right tetration of 2, complicated, I know, is the same as the left pentation of the left hexation of the double right pentation of 2. So Just what does that mean? It means that 2, just any number of hyperoperators, LL, whenever you take 2 steps to the left, and equals 2H. This is the property that generalizes to all levels of the hyperoperation hierarchy. The whenever you take, you know, this is the property that generalizes that I'm calling left equivalency for now. This is the property that generalizes. And basically, the reason that this generalizes like this, taking 2 steps to the left at any time is the same as taking a right step and a left step. The reason that this generalizes is whenever you do powers of 2 is simply because 2, it, it's just a consequence of this property. Equals XHR2. I don't really know how to prove this. I don't really know how to talk about this. But I'm just excited. Because, like, this seems like a genuine algebraic property. It's a bit weird that it involves the number 2. Um, but it's a kind of structure that applies to the whole hyperoperation hierarchy. And it's built off of this other level of structure. But I just feel like, something can be used, something can be done with that to find, you know, to find other function. I don't know how to say it. Something can be done with this, is all that I'm saying. And, um, I hope that you understand this video, and I hope someone is able to explain it better than I can. I hope someone's able to prove it properly. But this is what what I'm saying is a property that applies to all levels of hyperoperations. Whenever you take 2 as the base number for any hyperoperation, and you take any hyperoperation sequence, whenever the last 2, movements in the hyperoperation are left movements, it's the same as making them a right and a left movement. Just for a base of 2, though. This doesn't work for 3 or for any larger integer, because, for example, 3 double pentated to the 2, for example, just equals 3 tetrated to the 3, 3 left tetrated to the 3, which equals 3 to the 3 to the 3, which equals 9 to the 3, whereas 3 right left, tetrated to the 2 equals 3 right tetrated to the 3, which equals 3 to the power of 3 to the power of 3, which equals 3 to the power of 9. And this is equal to 81. And this is equal to something much larger. So, Yeah, this left equivalency only works for the hyperpowers of 2, but even though it is limited to the hyperpowers of 2, um, I think I think there's still something there that might be able to prove that might be able to just advance the study of hyperoperations in the future. And I also want to add a conjecture just to the end of this. Uh, and that conjecture that I would like to see proved, uh, this is what I want to call. This is a unrelated conjecture, um, but for um, what do you call it? This is an unrelated conjecture, but it's still related to hyperoperations. So the hyper isolation conjecture. What this basically, what am I talking about? So I'm just going to say that based on my study of hyperoperations, I am pretty sure that every time you have a unique X hyperoperated, let's specify X right hyperoperated to the Y, that every unique pair of X and Y produces a unique value so long as X does not equal 1 and Y does not equal 1. So what I'm saying is that whenever you take any given base, B, and you raise it in a given hyperoperation to a power Y, and this is, of course, after exponentiation and only the right variance, so that's right tetration, that's canonical right tetration, left pentate, canonical right tetration, right pentation, right hexation, whatever, that whenever you take B hyperoperated to some power P, every single base is going to have unique hyperpowers after their first power. Because, of course, whenever you have a number that is a hyperpower, like, say, 65,536, 65,536 can, of course, be represented as 2 right tetrated to the 4. But 65,530 but it can only be represented as 2 right tetrated to the 4, and under the right tetration, it can only 65,536 right tetrated to the 1. There are no other integer representations of hyperpowers. And I am saying that this is true for every hyperpower. In every right hyperoperation. I'm not saying that this is true for left tetrations and left pentations and mixed hyperoperations, just the canonical right hyperoperations. And the reason that I just think this is interesting. I think this is probably true. I don't see a way for, the hyperpowers of 4 to ever align with the hyperpowers of 2 or the hyperpowers of 8 or anything like that. I think that all strings of hyperpowers are unique after, of course, the first item in the list, which I think if this is proven, it will also have It could also be useful for discerning some things with hyperoperations. So, that is the thing that I want to talk about in this hyperoperation video. Um, I hope someone makes a better version of this because I don't know how to, and I don't have the patience to. But I hope this inspires someone to study this more and to make a better version. So, bye bye.